everyone and welcome back. In the previous session, we discussed the fundamentals of hypothesis testing, including null and alternative hypothesis, significance levels, p-values, one-tailed and two-tailed tests, and the step-by-step procedure involved in testing hypothesis. In that discussion, you may have noticed that we referred to several statistical tests such as the t-test, z-test, chi-square test, and ANOVA. In today's session, we take this understanding one step further by answering an important practical question. How do we decide which type of statistical test to use? To answer this, we introduce the concepts of parametric and non-parametric hypothesis testing. By the end of this session, you will be able to understand what parametric and non-parametric tests mean, identify the assumptions underlying parametric tests, recognize when non-parametric tests are appropriate, clearly differentiate between parametric and non-parametric hypothesis testing. Let us begin with parametric hypothesis testing. Parametric hypothesis tests are statistical tests that make specific assumptions about the population parameters from which the sample data is drawn. The word parametric comes from the term parameter, such as population mean, population variance, and population standard deviation. In parametric testing, hypotheses are formulated and tested about these population parameters. For example, is the population mean equal to a specific value? Is the difference between two population means statistically significant? Parametric tests rely on a set of assumptions. The most important ones are normality, that is, the population from which the sample is drawn is assumed to be normally distributed. Interval or ratio scale data. The variables should be measured on an interval or ratio scale such as height, weight, income, test scores, or productivity. Homogeneity or variance. When comparing groups, the population variances are assumed to be equal. If you see here, there are three normal distribution curves with different means, but the same standard deviation and hence the same variance. This is what is meant by homogeneity of variance or homoscedasticity. The next assumption is independence of observations. Each observation in the sample should be independent of the others. When these assumptions are reasonably satisfied, parametric tests are powerful and efficient. Some commonly used parametric tests are z-test, which is used when the population variance is known and sample size is large. T-test, which is used for comparing means when population variance is unknown. The ANOVA or F-test, used for comparing means across more than two groups, and the Pearson's correlation, which is used to test linear relationships between continuous variables. These tests are widely used in management, economics, engineering, and social science research. Let us look at some typical use cases of each. The z-test is applied when the population standard deviation sigma is known. The sample size is sufficiently large and the variable is measured on an interval or ratio scale. A factory claims that the average weight of cement bags is 50 kg. The population standard deviation is known to be 1.5 kg. A quality inspector randomly selects 40 bags and finds a sample mean of 49.4 kg. The research question states, is the average weight of cement bags significantly different from 50 kg? Why is z-test appropriate here? Because the population standard deviation and hence the population variance is known. Sample size is larger than 30 and the variable, that is weight, is continuous. A government report states that the average household electricity consumption in a city is 250 units per month with a known standard deviation of 30 units. A new survey of 50 households reports a mean of 240 units. The research question is, has average electricity consumption changed? And the test used is Z-test for population mean. In this case also, you may note that the population variance is known, the sample size is more than 30, and the variable is average household electricity consumption, which is a continuous variable. The t-test is one of the most widely used parametric tests in applied research. It is used for comparing means when population variance is unknown. The one sample t-test tests whether an unknown population mean is different from a specific value, while an independent samples t-test, also called the two-sample t-test, compares two sample groups to determine whether their population mean values are significantly different or not. The paired samples t-test, also called the dependent sample t-test, is used to find out if the difference in the mean of two samples is 0. The test is done on dependent samples, usually focusing on a particular group of people or things. In this, each entity is measured twice, resulting in a pair of observations. Let us look at an example of a one-sample t-test from education research. A university claims that the average score in a statistics exam is 65 marks. A lecturer believes the performance of the current batch is different. A sample of 20 students has a mean score of 69. The research question here is the average score significantly different from 65? A t-test is done here since the population variance is unknown and the sample size is less than 30. An independent samples t-tests is done when a company wants to compare productivity levels between employees who have received training and employees who did not receive training. The research question here is there a significant difference in mean productivity between the two groups? Why a t-test? There are two independent groups, continuous outcome variable, which is the productivity score. An example of paired sample t-test from health research is as follows. A fitness program measures cholesterol levels in participants before and after a 12-week exercise plan. The research question is, does the exercise program significantly reduce cholesterol levels? A paired t-test is done here since the same subjects are measured twice and the mean difference in the cholesterol levels before and after the event, which in this case is the 12-week exercise plan, is tested. Let us now see when the analysis of variance, ANOVA or F-test, is done. ANOVA is used for comparing means across more than two groups by testing the null hypothesis that all group means are equal. A one-way ANOVA analyzes the effect of a single factor on multiple independent groups, and a two-way ANOVA is used to assess how two independent variables affect a dependent variable simultaneously. Let us look at an example from education research where a one-way ANOVA is used. A researcher compares student performance across three teaching methods: traditional classroom teaching, online learning, and blended learning. The research question here is, do mean exam scores differ across the teaching methods? One-way ANOVA is used here as there are more than two groups. The dependent variable exam scores is continuous and it measures the effect of a single factor, that is teaching methods, over three independent groups. Another example is when a manufacturing firm compares machine output across 4 production shifts. Here, the research question is there a significant difference in average output across the shifts? One-way ANOVA is used here as it involves comparing the means across more than two groups. Now, let us look at an example from marketing research where two-way ANOVA is used. A company wants to assess the influence of two advertising strategies, social media and television, on customer response among different geographical regions, urban and rural. The research question here is, which advertising strategy, social media or television, is more effective in generating customer response across urban and rural markets? Two-way ANOVA is used here. There are two independent variables, advertising strategy via social media and television, and geographical region, that is urban and rural, and a continuous dependent variable, that is customer response, which can be measured by sales conversion. Next, we come to Pearson's correlation. Pearson's correlation is used to test linear relationships between continuous variables and measures the strength and direction of the relationship. If the increase in one variable leads to the increase of the other variable, it indicates a positive relationship between the two variables. However, if the increase in one variable leads to the decrease of the other variable, it indicates a negative relationship between the two variables. Let us look at a few examples where Pearson's correlation is used to test hypotheses. The first example is human resource management research, in which a researcher examines the relationship between years of experience and annual salary. The research question is there a linear relationship between experience and salary? Pearson's correlation is used here as both variables are continuous and the researcher is interested in association and not causation. The next example relates to supply chain management. A logistics analyst studies forecast accuracy and inventory holding cost. The research question is, does higher forecast accuracy relate to lower inventory cost? Pearson's correlation is used here as the variables are continuous and the researcher expects the relationship between the variables to be linear. In social sciences research, a study explores the relationship between hours spent on social media and stress score. The research question is there a linear relationship between social media usage and stress levels? Let us take a quick look at all the parametric testing techniques discussed in this session. In short, if the goal is to compare means, use Z, T or ANOVA. If the goal is to study association, use correlation. Although we will be discussing about non-parametric hypothesis testing in more detail in the next week, let me introduce you to what it is and how it is different from parametric hypothesis testing. Non-parametric tests are statistical tests that do not assume a specific distribution for the population data. Unlike parametric tests, Non-parametric tests do not require the assumption of normality, and they do not rely on population parameters such as mean and variance. Instead, they are often based on ranks, signs, and frequencies or counts. Because of this, non-parametric tests are also called distribution-free tests. Non-parametric tests are particularly useful when the sample size is small, the data is not normally distributed, the data contains outliers or skewness, the variables are measured on nominal or ordinal scales. For example, in cases where customer satisfaction is measured using Likert scales, or preference rankings are collected, or categorical responses are collected using a questionnaire. In applied research, these situations are very common, especially in social sciences and management studies. Some widely used non-parametric tests are chi-square test for testing association between categorical variables, Mann-Whitney U-test, a non-parametric alternative to independent samples t-test, Wilcoxon signed rank test, an alternative to paired t-test, Kruskal-Wallis test, which is an alternative to one-way ANOVA, aligned ranks transformation ANOVA or ART-NOVA, and the Scherer-Ray-Hare test, alternatives to two-way ANOVA, and the Spearman's rank correlation, which is an alternative to Pearson's correlation. These tests allow hypothesis testing even when parametric assumptions are violated. Let us now clearly differentiate between parametric and non-parametric hypothesis testing. Parametric tests assume normality and known population characteristics. Non-parametric tests make minimal or no distributional assumptions. Parametric tests require interval or ratio data, while non-parametric tests can handle nominal and ordinal data. Parametric tests are more statistically powerful when assumptions are met. Non-parametric tests, on the other hand, are less powerful but more robust. Parametric tests involve population parameters such as mean and variance. Non-parametric tests rely on ranks, medians, or frequencies. Choosing the correct category of test directly affects the validity of research findings. To choose between parametric and non-parametric tests, researchers should ask the following questions. What is the level of measurement of my data? Is the sample size sufficiently large? Does the data approximately follow a normal distribution? Are there extreme outliers? If assumptions are satisfied, parametric tests are preferred. If assumptions are violated or data is ordinal or categorical, non-parametric tests are safer and more appropriate. To summarize today's session, parametric tests rely on population parameters and distributional assumptions. Non-parametric tests are distribution-free and assumption-light. Both play a critical role in applied research. Correct test selection ensures valid, reliable, and defensible conclusions. In the next session, we will apply these ideas using numerical examples and software outputs to help you gain hands-on understanding. Thank you, and I will see you in the next session.